Okay, so I want to use this video to go through the notes on page 108. And it's going to start talking about an indefinite integral. And so the first thing we want to reference is your homework on page 107. One of the things it asks you to do is to graph some accumulation functions. And so each of the accumulation functions, we're measuring area under the constant function 2. And they just had different starting points. And I just sort of recap that here on our notes here so that we can see that, g of t started accumulating at -2. And so here was g of t. And then h of t started accumulating at 0. So there was h of t. And then k of t was starting to accumulate at +2. And so there's k of t. And when you sketch those data points, you got 3 parallel lines. And, the fact that they're all linear, we could easily come up with their equation. Look at the intercepts and look at the slope. So it looks like g of t has an intercept of 6, and it's up 2 over 1, up 2 over 1. H of t has an intercept of 0, and it looks like it's up 2 over 1, up 2 over 1. Oh, sorry, up 3 over 1, up 3 over 1. And then same thing with k of t, up 3 over 1, up 3 over 1, with a intercept of -2, 4, and -6. So I can come up with an equation that would model each of these functions. So g of t would be 3x plus 6. H of t would just be 3x plus 0. And then k of t would be 3x minus 6. And it says, based on these results, any accumulation function measuring area under the curve of 3 will at least be of the format, like 3x, but then it'll be like some constant depending on where you started. So it'll be of the format 3x plus some constant. And this constant's going to depend, where did you start your accumulation? But notice that all of them would be of the same family of function that have this slope of 3. Okay. Now, similarly, I'd asked you to do a graph here for h, g, and k of an accumulation function under 2x. And so, and again, I've highlighted them here. I've taken that picture from Canvas, and each of these, again, have the same shape, right? It just, where was the y-intercept? And that all depended on where you started your accumulation. And so h of t, it has an intercept of 0, and it's actually, if you look at the data points, like 1, 1, 2, 4, 3, 9, 4, 16. Oh my goodness, it's x squared. So this is x squared plus 0. The next one, g of t, is it's like x squared, but it's looks like it's -4. And then k of t would be x squared. It looks like, if I'm reading that, minus 16. I can read my screenshot there. And even though maybe like the intercepts are changing, any accumulation function under the graph of 2x will be of the format x squared plus some constant. And again, that constant sort of depends on where you start your accumulation. And so again, there's this kind of like merging of worlds here. We're looking at accumulation functions. We're looking at area. All of a sudden, like we're somehow thinking about, wait a minute, what's the relationship here? There's a derivative relationship, right? Because what's the derivative of 3x? 3. And that's what we were measuring area under the curve. What's the derivative of x squared? 2x. And that's what the area under the curve that we were measuring. So there's definitely a connection here. Based on the 2 examples, we now know that accumulation functions, or finding area under the curve, is related to undoing derivatives. So we now know that finding area under the curve, finding area under curve, is related to undoing these derivatives. And it's the first part of what we're going to call the fundamental theorem of calculus. Okay, so again, there's this connection, right? What do derivatives and area and what we've been working on, how are they all connected? And just to kind of give you symbolically, like what we've seen, this right here is an accumulation function, right? We start at some constant c, and we are looking for area starting at that c to some point that we then define, and we'll get an area value. Now, let's say you don't see the accumulation pieces. Let's say you just look at the inside part. This right here is some kind of antiderivative, and we can at least answer it up to a degree, up to a point of certainty, by we can say, well, this right here is going to be x squared plus some constant depending on where we start. So I want to kind of make sure we understand the two. Like I can get a definite answer here because it's an accumulation function measuring area at a fixed point. Here, this is just basically interested in, well, an antiderivative. In other words, just give me the family of functions that I would have gotten if I knew what my accumulation function was. It's undoing a derivative. Look at that relationship. This here, if you take its derivative, it should have been what you started with. And you know, like you might say, well, what happens to that c? Well, what's the derivative of a constant? It's going to be 0. So that's kind of what I want to make sure that we kind of put together. And then in the next video, we'll just look at some examples.